Because it's 10 o'clock, so we probably should get started. Great to see you all, and good morning, or rather, well, good morning to those in Europe, and good afternoon to those listening in from Asia, and very early good morning to those possibly calling in from North America. This is the One World seminar series on signal processing. My name is Eric Larsson, and I'll be the moderator today. Our guest and speaker today is Angel Lozano from UPF Barcelona, Spain. So Angel received his doctorate from Stanford University, and then he spent 9 years at the Bell Labs in New Jersey, after which he returned to Barcelona, where he is now a professor at UPF. So Angel, good morning. How are you today?
Hey, Eric. Good to see you.
All right, so great to have you here. So your talk today is going to be on MIMO, and specifically on line-of-sight MIMO, an old theory up to new tricks. I think without further delay, I'll give you the floor, and Angel will speak for perhaps 30-40 minutes. And during his talk, feel free to pose questions that you can write in the chat. And after the talk, we'll sift through the questions, and there'll also be opportunity, of course, for those who want to open their mic and speak. So with that, I think welcome again, and greatly looking forward to your talk, Angel.
Okay, thank you, Eric and Marius, for inviting me to participate in this prestigious forum. I'm honored, and I hope that my presentation will be of interest. It should take about 35 minutes, no more. And parts of this work are the fruits of collaboration with my colleagues Hidongdo and Nam Yong-Lee from POSTECH in South Korea. It's a real treat working with them. Okay, here's the outline. The presentation has 3 parts, but a couple of them are fairly short. So most of my time will be spent on part 2, which is the main thrust of what I want to convey. But to get there, I'd like to take you first to a quick retrospect, and bear with me, it will be short. So here we go. To put things in context, a bit of a look back at how MIMO came to be. I wrote a textbook on MIMO with my friend Robert Heath, and as we're both history freaks, we had a section on the origins of MIMO, and for that we spoke with all the key players. We were interested in pinpointing the eureka moment when somebody had the key insight that made MIMO possible. But what we found is that tends to be the case. There is no clean eureka moment. Rather, there was a period of time when ideas and advances that seemed disconnected converged in a series of steps. So credit for MIMO should be widely distributed, but a few individuals do deserve special mention. And despite the absence of a single epiphany, it's very instructive to look back at this. So first, let's see what the mindset was before MIMO. Consider an array with antenna spacings d, receiving a signal from a point source in line of sight. The phase shift at the end receive antenna is simply what we have up here, where lambda is the wavelength and this band is the distance between the source and the nth antenna. With a bit of trigonometry, this band can be written like this at the bottom as a function of the distance d sub 0 for some arbitrary reference antenna and the angle theta relative to the axis of the array. Virtually always the source was considered sufficiently far for the wavefront to be locally flat over the array. And then this band is approximately d sub 0 plus n times d times cosine of theta, meaning that the phase shift equals a constant term that depends on d sub 0 plus the linear phase shift across the array. By reciprocity, what applies to reception also applies to transmission. So the time-honored paradigm was to regard the wavefronts as planar at both ends of the links. That means that there's a common phase dependent on the distance d sub 0 traveled by the plane wave, and then there's a linear phase shift across the transmit antennas and a linear phase shift across the receive antennas. Most importantly, the linear phase shift across the transmitter is the same from the perspective of every receive antenna and vice versa. These phase shifts only depend on the angles between the arrays and the plane wave. The angles are these theta t and theta r, and on the antenna spacings. It follows that the channel matrix connecting n sub t transmit with n sub r receive antennas is the outer product of two vectors. So it is rank 1 matrix with a single non-zero singular value. This channel can represent any line of sight situation with arrays at both ends having any arbitrary orientation and any antenna spacings. And the formulation is even extended to 3D settings with an additional angle. The one assumption, once more, is that the wavefronts are locally flat at both transmitter and receiver. By applying to a signal some phase shifts across the transmit array that are the conjugate of the channel's phase shifts, at that end, a beam can be created that points to the receiver and vice versa. By the receiver combining the observations with phase shifts that are the conjugate of the channel's phase shifts at that end, a beam is created that points to the transmitter. So mathematically, these beams focus this one signal on the channel's eigen direction corresponding to the non-zero eigenvalue, single value. This idea was implemented in the form of phase arrays as far back as the 1950s, and then refined into adaptive arrays where not only the phases, but also the amplitudes were adjusted. And by the 1980s, refined into smart antenna arrays whose patterns could further null out interference. All of these are effectively special filters that rely on coherence across the arrays. A key attribute of all these architectures is that each array acts as one degree of freedom. It launches or it receives one signal, weighted at each antenna with the premise that the individual antenna transmissions cannot be discerned because the range is too large compared with the antenna spacings. So each array looks like a single point when seen from the other array. This was the paradigm till the 1990s. Line of sight was seen as desirable because it ensured coherence across the arrays and the best possible path loss, whereas multipath propagation was seen as disruptive of coherence and of path loss. And so countermeasures were devised in the form of diversity. By the 1990s, multipath propagation and fading had become a major issue. And these two gentlemen at Bell Labs decided to join forces and investigate possible solutions. Jerry Foschini, an information theoretician, and Mike Gans, an expert in antennas and electromagnetics. So they set out to answer this question: what is the optimum antenna for a multipath channel from an information theoretic perspective? They considered antenna arrays with no restrictions on how to transmit or receive. And they considered the worst possible multipath channel where the matrix has IID entries, so no coherence whatsoever. The result was that the optimum strategy was to transmit an independent signal from each antenna, what we now call spatial multiplexing. This, which we now take for granted, was quite shocking at the time. Jerry Foschini used to explain that the first time he gave an internal talk about this, people said that it would never work because the different signals would drown each other and could not be recovered. It wasn't until prototypes were built that these concerns were dispelled. Spatial multiplexing was radically novel in that it sought to exploit rather than to counter the effects of multipath propagation. And one can view this from multiple perspectives. So let's spend a few seconds on two of these perspectives, one having to do with linearly independent relationships, and the other one having to do with apertures and lensing. If we view multipath components as discrete, then the key insight is that each one provides a different linear combination of the transmit signals at every receive antenna. Intuitively then, the number of degrees of freedom is determined by the minimum of the number of transmit antennas, the number of receive antennas, and the number of multipath components. This, of course, provided these multipath components are sufficiently different in number of wavelengths for their phases to be distinct, because otherwise they are redundant. In contrast, if we view the multipath channel as a continuous spectrum of diffuse power, then a better perspective is that of the multipath channel acting as a lens. Here. A lens, an aperture much bigger than the arrays themselves, and which enables the transmitter to resolve the receiver, each of the receive antennas, and vice versa. So in this case, what matters is the angle spread, which in essence is the angle subtended by this environmental aperture from the arrays. Well, whichever the interpretation, the key point is that with special multiplexing, we get to activate multiple degrees of freedom, and that's what excited people very much. In fact, in that excitement, for some time, it seemed as if line of sight propagation was suddenly undesirable. And I remember vividly some discussions with people asking as to whether in a line of sight situation, we should deploy some obstacle, say a tree, to break the line of sight and facilitate the emergence of multipath. And well, we know that it's not quite so, because there's a trade-off. So line of sight yields the most received power, but only 1 degree of freedom. With multipath, we have a lower received power, but multiple degrees of freedom. So that trade-off is an excellent starting point to discuss Nanoscience MIMO, which is the subject of this main part of the presentation. Excited about special multiplexing, some inquisitive minds wondered shortly after the Foschini-Gans paper was published already about the possibility of reaping the benefits of special multiplexing in the absence of multipath. In fact, Gans himself made some observations about that in a manuscript that was circulated within Bell Labs, but not published outside. In essence, he realized that you could specially multiplex in line of sight conditions, provided you brought the arrays close enough. At that time, it didn't seem possible to ever go beyond frequencies of 2 or 3 gigahertz, for which his calculations showed that the arrays would have to be within tens of centimeters of each other. So his observations were rendered a mere curiosity. An alternative to bringing the arrays very close was to make the antenna spacings within the arrays very big, because, well, the effect of a multipath component is identical to the effect of having mirror images of the transmitter and receiver, and so a much bigger aperture. So Foschini himself entertained this possibility of arrays with very big spacings, really big arrays, with Peter Dreesen from AT&T. And in 1999, they published this paper on the capacity formula for multiple input, multiple output wireless channels, a geometric interpretation, where they identified settings and geometries that made special multiplexing possible in line of sight. For instance, having different base stations act as a single array. The paper didn't get much attention back then, yet in hindsight, it was an important piece of work, with the recognition that geometry was very important for Nanoscience MIMO, and even with this embryonic concept of base station cooperation. But the main takeaway point was that Nanoscience MIMO just wasn't possible with compact arrays in the conditions of systems back then. All right, so fast forward 22 years, the 6 gigahertz boundary, which seemed like a hard boundary back then because of propagation, has been broken through. And, we found that propagation isn't so terrible after all. So we're now operating commercially at millimeter wave frequencies, and researchers have their eyes set already on sub-terahertz frequencies with wavelengths close to or at 1 millimeter. So an array of a few centimeters is now huge in terms of wavelengths. At the same time, transmission ranges have shrunk dramatically. We've gone from macrocells down to microcells, picocells, and even femtocells. Somehow we skip nanocells, which is something that I always had me wondering, but never mind. And of course, we have Wi-Fi, Bluetooth, etc. So we still have traffic going over the macros, but most of the wireless access these days is over short hops. So the conditions in which we operate have changed dramatically, and the question arises of whether the classic paradigm of planar wavefronts still applies. And the answer is that, well, there are a growing number of situations in which this paradigm needs to be transcended, because the curvature of the wavefront over the arrays cannot be neglected. We conducted this experiment at 300 gigahertz, where the transmitter was fixed, and we displaced the receiver over 15 centimeters at a range of 2 meters. And the measured phase is plotted here on the right. And you can see not only how it is curved, but it nicely fits a quadratic expansion of a sphere. So we can just regard the wavefronts as quadratic rather than linear. To get to the essence of things, we can see what the antenna spacing would have to be in this two antenna toy setting for the direct distance d sub 0 and the cross distance d sub 1 to differ by a quarter wavelength. So the phases are sufficiently different. At 2 gigahertz over 1 kilometer, which is typical of the situations that Foschini and Driesen considered, the antenna spacing would have to be at least 9 meters. But at 140 gigahertz over 20 meters, that has shrunk to 14 centimeters. And at 300 gigahertz over 10 meters, it's only 5 centimeters. So we could activate as many as 16 degrees of freedom with a planar array of only 15 by 15 centimeters. Here on the right-hand side, you can see the combinations of range in meters and frequency in gigahertz, for which the planar wavefront representation is deceiving in the sense that there is enough curvature to have at least 2 degrees of freedom. And the region where that happens is indeed rather broad. There are many potential applications where this combination of high frequencies and short range might make sense, say Wi-Fi and indoor systems, information kiosks, wireless interconnections, UAV communication. In all these applications, MIMO may be possible over line of sight channels, which is welcome news because at high frequencies and over short ranges, the channel is very often line of sight. In fact, referring back to the trade-off between path loss and DOFs in multipath channels, with line of sight MIMO, it seems like we can have our cake and eat it. The best possible path loss and multiple DOFs. The major difference between MIMO and multipath environments and line of sight MIMO is that here geometry is king. In a multipath channel with power incoming from all directions, it doesn't matter that much how the arrays are oriented, but in line of sight MIMO, when the power arrives from only one direction, it definitely matters. Here, the transmission range, the antenna spacings, and the array orientations completely determine the channel matrix. In that sense, it's instructive to consider uniform linear arrays, from which a lot of intuition can be extracted. So I'm going to do that for now, and later I'll extend that intuition to planar arrays. So ULAs correspond to segments, and we need 3 angles to represent any relative orientation of 2 segments. We need the elevation of the transmitter, say with respect to this x-axis, the elevation of the receiver, and a relative azimuth between the two. Now, a very welcome fact is that this relative azimuth does not affect the singular values, which depend only on how the 2 arrays project on a common plane. So to examine the information theoretic properties of the channel, we can set this azimuth to 0. So the quantities that matter are the elevation of the transmitter, theta t, the elevation of the receiver, theta r, the respective antenna spacings, d sub t and d sub r, numbers of antennas, the range, capital D, and of course the wavelength, lambda. The channel matrix depends on all these quantities and in a very structured fashion. So sorry about that. PowerPoint decided to quit on me. All right. So in a very structured fashion, the channel matrix let's see. All right. The channel matrix looks like this. It's a Van der Waals matrix that you can see here, pre and post multiplied by diagonal matrices of phase shifts. This diagonal matrix, DRX and DTX, can be compensated by the transmitter and the receiver with per antenna phase shifts. So effectively, the channel is this Van der Waals matrix in the center, where N sub max here is the maximum of the transmit and receive antennas. And the only thing that appears in this channel matrix is this parameter eta, which you can see here at the bottom, a single parameter that combines the array orientations, the antenna spacings, antenna spacings, number of antennas maximum, wavelength, and the range. So this one parameter alone determines the Nanoscience MIMO channel, which is super convenient. This eta depends on both innovations, transmitters and receivers, but what actually matters only are the relative orientations. So again, without loss of generality, we can set the transmitter innovation to 0, finally obtaining this simplified form for this all-important parameter eta. Now, looking at eta, if we let the range d go to infinity, then we're back in the planar wavefront paradigm. So eta becomes 0, and the rank of the channel becomes 1. But once d, the range, backs off from infinity, eta starts to grow beyond 0, and the rank of the channel also starts to grow as we capture the richness associated with the curved wavefronts. But now the question is, would we want eta to be as high as possible, or is there some sort of optimum value? Well, there is a value that makes things very special, which is eta equal to 1. This particular configuration is unique in that the channel then adopts the form of a Fourier matrix. Not only is it full rank, but all the single values are equal, and the rows or columns, depending on whether the matrix is fat or tall, are orthogonal. So then a set of standard beams suffices to communicate as many DOFs as antennas without any interference. So in that sense, this is just about the perfect MIMO channel. So we have that for vanishing eta, which corresponds to the range going to infinity, the wavefronts become flat and the channel is rank 1. This is the classic paradigm. For positive eta, which corresponds to a finite range, the rank becomes richer up to this special value of eta 1, which corresponds to this very specific range in here, for which not only is the rank full, but all the single values are equal and the channel has this Fourier structure. This full rank special nature of the channel obtained for eta equal to 1 has been the source of a lot of interest and research in recent years, almost to the point of becoming an infatuation. So people are drawn by the promise of all these DOFs. But one must be careful and never forget that there is a key variable that determines everything in communications, and which you may have noticed I haven't mentioned yet, which is the SNR. So yes, having as many DOF as possible is fantastic at high SNR. And we have plenty of power to load all these degrees of freedom. Conversely, at low SNR, what matters is to maximize the receive power. And the optimum strategy is then to activate a single DOF through beamforming. So at low SNR, the larger is the maximum single value, the better, because the better are beamforming. So here's where this gets really interesting. If we reasonably consider that the sum of the square single values is constant for just for conservation of power, then we have that at high SNR, we want a full rank channel where all the single values are equal, which corresponds to eta 1, and corresponds to a pronounced and very specific curvature of the wavefronts. But at low SNR, we prefer a rank 1 channel, which with just one strong single value. This corresponds to eta 0 and to planar wavefronts. And at medium SNR, we want a partial rank, which corresponds to eta between 0 and 1, and to a moderate wavefront curvature. So at each SNR, we would like to see a different parameter eta, which, recall, depends on the various geometric quantities as per this relationship at the top. Now, in classic MIMO, we're being used we're used to the channel being given to us by the multipath environment. But here in Nanoscience MIMO, we can actually exert direct control over the channel by adjusting one or several of these quantities that make up eta. So conceivably, we can configure the channel depending on the SNR. And since every channel has its capacity, configuring the channel by adjusting eta, we would obtain a sort of meta capacity. So we would have the usual optimization over the transmit signal, X, for each possible channel. And then we would have an outer optimization over the channel itself. So this is a whole new aspect of Nanoscience MIMO. And a very nice result we derived with the people in PostTech was this upper bound on the meta capacity. So this is the highest possible capacity among all possible channels at any given SNR. It's a piecewise function that has a very simple form and depends only on the antenna numbers and the SNR. This is the best one can hope to do in a Nanoscience MIMO channel for a given number of antennas at each SNR. What's especially useful about this result, besides its simplicity, is how we derived it, which is by finding the optimum channel at each SNR. And as it turns out, this optimum channel has a number. This optimum channel has a number of non-zero single-mode values, all identical, and the rest of the single-mode values are 0. So here at the bottom, you have this optimum number of non-zero single-mode values as a function of the SNR. Again, is a piecewise function. And here's a picture showing them. So for SNRs below 3.9 divided by the product of the antenna numbers, it's optimum to have in the channel just one non-zero single-mode value on which to beamform. After that, the number of non-zero single-mode values should start increasing with the square root of the SNR and the square root of the antenna numbers. And until the maximum value, the maximum number of non-zero single-mode values is reached at an SNR of 3.9 times n min divided by n max. So that's the ideal channel. Now, how about the actual channel we find in Nanoscience MIMO? Well, here's another nice result, which is that the Van der Waals matrix spawned by ULAs exhibits a concentration of the single-mode values as the number of antennas grow. So there are approximately n min times eta non-zero single-mode values. Remember, this is the form for eta, and this is the minimum of nt and nr. So as the number of antennas grows large, this approximation becomes exact. So let me show you that with an example. Suppose we have 16 transmit and 16 receive antennas. These are the 16 single-mode values for 3 different values of eta, so 3 different orientations, antenna spacings, distances. And you can see how the number of them that are non-zero is approximately eta times 16. And the rest are negligible. So if we increase the number of antennas, we would see this transition sharpen, and the single-mode value distribution would adopt the form of a step function. So in the limit, with many, many antennas, we would get something like this, step functions, where the transition point depends on eta. So putting these 2 results together, we have that the optimum channel has a certain number of single-mode values, all identical, and that number depends on the SNR. We call it by this. Whereas the actual channel has approximately eta times n min non-zero single-mode values. So in the ideal channel, the number of single-mode values, the non-zero single-mode values depends on the SNR. In the actual channel, depends on eta. It follows that if we can match one thing with the other, we can have the actual channel approximate the optimal channel and approach the meta capacity upper bound, and even achieve it asymptotically in the antenna numbers. So all we have to do is set eta, so equate these 2 results. So set eta equal to the optimum number of single-mode values divided by n min. That means that we have to make eta a function of the SNR. So we have to configure something in the channel, something in the geometry as a function of the SNR. Here's an example again for 16 transmit and 16 receive antennas at an SNR of -6 dB. the ideal channel giving rise to the meta capacity upper bound has 4 non-zero identical single values. The other 12 are 0. If we set eta equal to 4 divided by 16, which is 0.25, then the channel created by our ULAs will have these single values on the right, which approximate pretty well the ideal situation. And like I said, if we have more and more antennas, this approximation will become exact. So we have to configure eta as a function of DSNR. And to do that, we can in principle play with any of the factors, any of the quantities within eta. Now the wavelength and the number of antennas are typically fixed, and the range D is often not under our control. It depends on the application. So one possibility is to configure things by adjusting the antenna spacings, little d t and little d r. This figure shows how that works. The dashed line, barely visible, is the meta capacity upper bound. And all these solid lines correspond to what is achievable with different antenna spacing with ULAs. At every SNR, there is a curve that basically meets the upper bound, indicating that if somehow we could finely tune the antenna spacings depending on the SNR, we would achieve optimality. So finally adjusting the antenna spacings is a very good option for applications where the SNR is fixed, and we can configure things once and for all. Now for applications where the SNR varies, we will need to dynamically adjust the antenna spacings, which is not something we can easily foresee. An alternative is to adjust the antenna spacings only coarsely by activating, depending on the SNR, one among a few arrays with different spacings, say 3 arrays, as in this picture. So at low SNR, we would activate array A, at medium SNR, array B, and at high SNR, array C. We don't do as well by switching between these curves, but it's an option that has been proposed and that could be practical. So the idea would be to have, for instance, the arrays, as in here, and depending on the SNR, we switch to one or the other. So here the vertical axis is the SNR and shows the intervals on which we'd use each of the 3 arrays. Low SNR tight spacings, medium SNR medium spacings, high SNR the magical spacing that makes the channel a Fourier matrix. Okay, so that's what we can do with antenna spacings, but we have another possibility to tweak eta, which is to adjust, rather than the antenna spacings, the orientation of one array with respect to the other. The effect is the same because what matters is the projection of one array on the other. So if the transmitter is vertical, then the action is going to be on the vertical dimension. So if the receiver is rotated away from vertical, then this projection squeezes the antenna spacing, as in here, and renders them effectively small. That's what we want at no SNR. Now, as we rotate back towards the vertical, these projected spacings increase, and in the end, with no rotation, the actual spacings take effect, which is what we want at high SNR. So if we imagine a receiver whose array can be rotated, or where we can select one among several rotated arrays, as in this cartoon, then we can reconfigure eta by doing that as a function of the SNR, and that's going to ensure optimum performance. Here's an example for an SNR of 0 dB. The figure shows the spectral efficiency, bits per second per hertz, versus eta for array sizes of either 32 or 256 antennas at either end. The dashed lines are the meta capacity upper bounds for each case, and the solid line is what ULAs achieve as they are rotated relative to each other, and eta sweeps the interval between 0 and 1 at the optimum point, which in this case is 0.5, eta 0.5. The upper bound is essentially achieved, even with the not so big number of 32 antennas. So reconfiguration through array rotation is totally effective. All right, so that brings me to the end of the second part, where I have concentrated on ULAs. So let me now zoom out and consider consider more general arrays. So to recap, we have seen that by configuring the antenna spacings and or the array orientations versus the SNR, UNAs can approach and asymptotically achieve, asymptotically in the antenna numbers, the meta capacity, which is the best possible capacity over all possible channels at any SNR. Now, an obvious question is, at this point, is whether this applies only to UNAs. And it's a relevant question because the form factor of UNAs is not always terribly convenient. Often a planet array is preferable to a UNA, and for the sake of specificity, we can concentrate on uniform square or rectangular arrays. The expressions become more cumbersome, but it's mostly a cosmetic issue because a square or a rectangular array can always be expressed as the Kronecker product of two perpendicular UNAs. So the channel matrix itself is the Kronecker product of the channel matrices corresponding to those UNAs. So each of these composing UNA channel matrices involves the number of antennas and the antenna spacings for the projection on that dimension. So we're going to have antenna spacings on the X and Y dimensions, here and here, the number of antennas on each dimension, here and here. This happens both at the transmitter and at the receiver. So we end up with two parameters eta, one on the X dimension and one on the Y dimension. So let's see how effective rotation is in this case. And to preserve the gains of the individual antennas, meaning that the antennas point at each other through their main lobe, we're going to rotate with respect to the z-axis, which is the one connecting the two arrays. Now, just by looking at the geometry, we can infer that the effect of rotation is going to be less pronounced here than with pure UNAs, because if you think about it, as one dimension rotates away from a certain direction, the perpendicular dimension rotates into that direction. So things are going to change as we rotate, but probably not that much. And indeed, here is the spectrum efficiency, again, bits per second per hertz versus SNR, with 16 transmit and 16 receive antennas, both arrays being 8 by 8 square. This is the meta capacity upper bound, and these various sonic curves correspond to different rotations. And as you can see, the effect of these rotations is minor, and except at high SNR, we don't get to hack the upper bound the way we did with UNAs. Here, we always short by 4 or 5 dB. So this is the situation. Because UNAs are one-dimensional, 2D rotation enables full control of the projection of the receiver on the transmitter. Now with 2D arrays, with planet arrays, that would require rotating in 3D, but that would point the main lobes of the individual antennas away, which would cost us a loss of power. So the question that pops up is, well, how can square arrays recover some of the virtues of UNAs? And the answer is, well, by making them more like UNAs. So this 4x4 square array, for instance, we can convert to an 8x2 rectangular array and then squeeze it vertically so that its form factor is not terribly different from the original array, but at the same time, it's decidedly more like a UNA. So let's see how that works. This shows the percentage of the meta capacity upper bound that can be achieved versus the SNR by configuring the arrays optimally, say rotate via rotation, for instance, at each SNR. Okay, so this is the best that we can do. At the top, we have the performance of a 64 antenna UNA, which essentially achieves the upper bound, 100% almost. It only falls slightly short because the number of antennas is finite. Far below, we have the performance of an 8x8 square array, which physically measures 24 centimeters by 24 centimeters. Here, no matter how we rotate it, we fall really short of the upper bound. Now let's see whether our idea to recover some of the shortfall works. So if we reshape the square array into squeezed 16 by 4, which measures 37 by 15 centimeters, we recover about half of the shortfall, which is very good. And we could still go one more step and reshape into a 32 by 2, further squeezed vertically to measure 54 by 7, okay, which performs pretty much as well as the ULA with a somewhat better aspect ratio. So depending on the specific application, we can choose the best solution in terms of the trade-off between performance and form factor. Okay, so coming to the end, and here are some parting thoughts. On a personal note, and after decades of working on MIMO in one way or another, I find that every time I think that MIMO is a done topic, well, we somehow find new things to do with it. In the case at hand, what happens is that as we move up in frequency, multipath declines, but the antennas become resolvable in line of sight. So we still have good MIMO properties. The flavor, though, is somewhat different because now geometry is king. So by configuring or reconfiguring the array geometries and the orientations, we can optimize the channel itself, and this is new. We used to optimize in the transmit signals for a given channel. Here we get to optimize both. And this is one more step towards this new paradigm of smart radio environments where people are proposing to deploy meta surfaces to control the channel. There's a lot of excitement about that, and I think that Nanoscience MIMO plugs in nicely as an ingredient. And I'd say that this may be a very fertile research area in the next few years for those who may be looking for a research topic. And as a final comment, even though I didn't have time to present the results we have on the matter, Nanoscience MIMO and reconfigurability via rotation continue to work with low resolution D2As and A2Ds, even with 1-bit converters. Just that in that case, we don't have the benefit of a meta capacity upper bound, or at least we have not been able to derive it. So again, a good open problem. This is the end of the presentation. Thank you so much for the attention, and back to you, Eric.
Thank you, Angel. It's a great and inspiring presentation. So, well, okay. Quite amazing indeed. I mean, the gains are rather substantial that you showed in your examples. I think we do have a number of questions in the chat, and let's see if I'll take them in the order that they appeared. So the first question is as to whether this new line of sight model is validated by any real world measurements. I don't know if there is much to measure here, because you're like this away from a point source as the model, but I'm sure you want to address the question.
No, I can, yeah, sure. So I think that most of the results we have seen, experimental results, are all in controlled environments. In this case, I showed the results of measurements we made, and we have a very nice setting where we isolated all possible reflections to concentrate on the line of sight component, right? And I think most results that I've seen are like that. So it's a legitimate question, right? So once you get outside, we never get a pure line of sight channel, we get Rician channels. So the question is, how is this going to work with a Rician channel when we have a dominant line of sight component, but also multipath, right? And I should say this is among list of research topics to explore. We know that multipath channels are good for MIMO, right? So I don't expect bad things to happen, but it could be that the optimization changes, right? Like maybe the orientations that are optimum are probably going to be different. So it's a very good question, and like I said, I'll get to it as soon as I have somebody who can work on it, and maybe other people can do that too.
Yeah, absolutely. So I think the real question is, I mean, whether in reality, we really will see free space line of sight propagation at all, right? So
maybe the closest would be the closest maybe if you're talking to a UAV, for instance, or really pointing towards the sky, right?
Yeah.
But
might not be a lot of scattering.
But in a Wi-Fi setting, for instance, I expect there'd be reflections of the walls and things like that. So lots of things to do here. Yes.
Right. Perfect. Yeah. Okay, great. So the next question is on antenna spacing and whether changing the antenna spacing would not also affect the mutual coupling between the antennas, and to what extent that has been taken into account here.
Yes. So the good news here is that we don't have to worry about it, because the smallest spacing happens at no SNR. It's a classic Land/2. And then as you go up in SNR, you want bigger spacings. Actually, you end up with spacing that can be quite big. I mean, at high SNR, you may want 5 or 10 wavelengths of spacing. So,
certainly, I mean, but I think at the heart of the question is that obviously going below half a wavelength can be a disaster, right? Unless you really model the coupling properly, and even if you do, I mean, it's hard, right? Because of various reasons. But now, if we go from half a wavelength and then up, let's say, to 5 wavelengths, I mean, at half a wavelength or 0.6 wavelengths or something like that, there is still some coupling, which presumably disappears when you go up to your 5 or 10 wavelengths. So it does seem like a phenomenon that would have to be taken into account.
There's
an accurate model here.
There's an interesting angle here, which is that the antenna spacings are pretty big. Are going to be pretty big because that's what you want to have. But the number of antennas can be also very big. So having so many antennas within a certain space, even if they're nicely spaced. So one wonders, right, if the accumulation of the couplings for many antennas that are nearby, even if they're weak, if the accumulation can be substantial.
There are many of them, yes.
So this is a question for which somebody who's an expert on electromagnetics. So I invite people who understand those issues to look at them, definitely.
Right, yeah, perfect, yeah. Okay, so the next question is that, I mean, the topology, I'm reading from the chat here. The topology required by the classic setup is communication distance dependent. However, you mentioned applications like UAV to ground, where the communication distance changes. And then the question is, what can be done to resolve this? I mean, because rotating the array doesn't seem like practical solutions in these scenarios.
It may be. I mean, for the UAVs is a good example, right? So in UAVs, rotating the array is very easy, right? I mean, the UAV just has to rotate itself, which is something it can do, right? So it's just that then the optimum orientation of the UAV will depend on the distance, right? If the distance is increasing, optimally you would want the UAV to be going away from you and rotating at the same time to maintain the optimum angle. If you want to preserve the perfect channel. Of course, I mean, you know, you're going to be trying to chase the perfect channel, but sometimes you're not going to have it. Then you're just going to compute the pre-coder for the channel you have, and you know, you get your performance. But at least you can improve the channel somewhat, and then pre-code for the better channel, right? So even if you cannot achieve the meta capacity upper bound, you can, by rotating, you can always get a better channel. You know, you're constrained by the distance and by things you don't control, but you can get a better channel, and then you can pre-code for the better channel. So it's so yeah, you can still do a lot of things here. And with UAVs, it's great. I mean, with UAVs, you can always optimize the channel if you can control the orientation. In other cases, you can, right? I mean, you know, if I'm wearing my tablet is the device. I mean, it's not very easy for me to have rotate my tablet optimally depending on the distance to the access point. So in some applications, it might not work.
Right.
Yes.
Yeah, very good. Okay. So the next question is that in massive MIMO, there exists a specific direction through which the signal strength is the most favorable in comparison with other directions. Could you please let us know about the last works gone over exploring the sparsity of the signal?
I'm not sure I get the question, because here the channel is as sparse as it gets, right? Single component.
Yeah.
Maybe
I also didn't understand the question.
We have to have McCann send us a clarification on this one.
Yeah. Okay, I'll move on through the questions in the chat. So the next one is whether the eta could be controlled by activating different numbers of antennas. I mean, controlling the Nmax is a function of SNR rather than varying the spatial and the angle of orientation. I think you did make a comment, or maybe.
Well, I mean, you can do that. I didn't do it. You could do that. It seems like a waste to switch off antennas if you have them, right? But certainly, yes. So if you switch off some antennas, you're going to lose some power, right?
Yeah, but it could be hardware savings potentially. I mean, if you have only a certain number of RF chains or something, and the possibility of switching.
Okay. Even if you disregard that,
it's very useful.
Yeah, even if you disregard the hardware power consumption, it is possible that what you gain from a better conditioning of the matrix, is more than enough to compensate for the loss of power. It's not impossible. I haven't looked at it. It's a very good question. And then, of course, if one takes a holistic view of the power consumption, then it gets more tricky. But yeah, no, it's sure. I haven't explored it. I've concentrated on the spacings and the orientations, but sure, you can play with this. I'd be keen to see what happens. Yeah.
Yeah, good. Okay, so another direction for potential future research in this field. So the next question is here: when the uniform rectangular array rotates relative to the transmit array, what is the main conclusion about capacity? I think.
Yeah. So what happens with URAs?
Yeah.
The URA structure is itself somewhat deficient, so you can't get the best possible channel with URAs, unfortunately. It's just because of their geometry. So you can rotate it and improve somewhat, but you always fall short of what you could do with UNAs having the same number of antennas. So the more you can make your URA one-dimensional, the more it's going to move one-dimensional, the more you're going to have control. You pay a price because sometimes it's not going to fit on your device, but you can play with the fact that you can squeeze it down. So what matters really is not so much the size, but that it has more antennas in one dimension than on the other. So you can squeeze it to make the size better to some extent. But the more it looks like a URA in terms of the antennas itself, not so much the centimeters, the more it's going to perform. It's a limitation of the geometry, unfortunately. And I don't know, circular arrays, for instance, give you nothing because you rotate them and you see the same thing. So, like I said, geometry is very important here, which is something I wasn't used to. Working in MIMO classically, geometry never worried about that. Work with UNAs because they're convenient, but we don't really care. We care a little bit because the delay spread determines things a little bit, but not like this. Here, geometry is everything. So it's something you have to get used to. It took me a while to.
So, I mean, related to that point, the question I was sitting on is like, I think all your analysis assume the scalar field, right? But in electromagnetics, we're going to have polarization also. So the antennas might be, well, could be linearly or circularly or have any polarization direction. And how would that interact with this rotation of the array and so forth? Could you comment on that?
I don't know. I've considered everything to be copolarized. It's a very interesting question because...
Yeah, but once you start rotating things around, I mean, you got to be careful, I think, right? Because the field itself is a tensor. I mean, it has an H component and an E component.
Yes, it depends on the type of rotation.
Yeah.
It depends on the rotation, on the axis of rotation. For some axes it matters, for some it doesn't.
Yes.
The same thing happens with the lobes of the antennas. For some axes, they keep pointing at each other. For some it doesn't. So in multiple channels, we know that the channel mixes up the polarizations nicely. But in nanosite, I would imagine it doesn't. So the polarization.
Yeah, as long as the antennas are oriented. I mean, if we think of like, I don't know, dipolar or simple linear antennas or something, as long as they're oriented properly, like lie in the same plane, should be fine, right?
Yeah.
And something to think about here, and particularly I think for the UAV application, because there you can't really control how the drone kind of aims. And
yeah, no, because the drone has. I mean, the drone has to worry about flying first of all.
Yeah, but maybe they could be resolved by having cross. I mean, whatever you call antenna here could be cross-polarized, perhaps element.
Yeah, I mean, if you replace one antenna with a cross poles, then you're safe, right?
Then you're safe.
The point is that we can take advantage of it somehow. Not just play defense, but play offense.
It's possible. Yeah. I mean, this is a highly interesting prospect. I think this idea of rotating the array to maximize the capacity, and it just felt like polarization at some point would have to play into the picture, right? And I mean, to model the electromagnetics properly, I think we have to, number one, work in 3 dimensions, and number 2, consider the polarization and the fact that the field is actually a tensor and not a scalar. But
this is down on my list of topics to explore.
Yeah. All right. So I think we're approaching the end. Any other questions from the audience? If not, then I'd like to thank you again, Angel. It's a great and inspiring talk, and it was nice to see so many here live listening in to this seminar.
Yeah, thanks everybody for coming in.
Thank you very much.
Thank you for inviting me. I'll see you in the next one, in that case as an audience.